Okay, so as of yesterday, we have discussed about this linear regression. So as I told you that linear regression algorithm, what it is, the aim is to find the best fit line to establish the relation between our independent and the dependent variable. So if I will go and check the linear equation, as we have been taught in our schooling also. So what is the equation of a linear line? That is y equals to mx plus c, right? That is nothing but y equals to mx plus c. So if we will go and check for this y equals to mx plus c, then my y is nothing but y equals to mx plus c. So here y is my dependent variable, or this is, I will tell it as my output variable, right? And this x are nothing but these are my data points, right? Or my independent variables upon which we are going to train. Okay, upon which my output data is completely dependent, right? So this m is nothing but this is my slope, right? This m is nothing but this is my slope of my line, and c is my intercept, right? Or it is my constant. So basically this c is nothing but, we will tell it as a constant, and we at maximum time we ignore this part because it is a constant. How much calculation we will do, okay, how much iterations we will do, so this c, particularly this c is nothing but it will remain constant throughout all your iterations, right? So what is the main thing, what is the main thing that we are going to compute? We are going to compute with this part, this mx. Okay, we are going to compute with this mx, right? Now if I will say that, okay, suppose as I told you that this is my, suppose I will here, I have some data points, and if I will draw a linear line, a straight line here, and I will mark my prediction point, okay, mark my prediction point just parallel to my actual points, then the distance between my predicted point and my actual point, this distance is nothing but this is my error. And what we have to do, we have to reduce this error. Okay, we have to reduce this error. Now whenever we are trying to reduce this error, what else we have to do with? So basically we have to deal with this beta 1 and beta 0 values, that means with my slope and my intercept. Okay, with my slope and with my intercept. So as if we are going to interchange these values again and again, we have to do the iterations, right? And whenever we are doing these iterations, at one point, I will be getting one theta value, right? One theta value, theta 1 value and one theta 0 value, where my this distance will be minimum, or I can tell it as approximately equal to 0. Okay, at that point of time, I can tell that, okay, this is my best fit line, okay, with my this theta 1 and theta 0 parameter. Okay, so for this iteration, for this, like whenever we are calculating the distance, right, we are iterating over different theta 0 and theta 1 values. So this process is called as the cost function. Okay, this function is called as my cost function. So here in cost function, what we need to solve, we need to do the summation of the distance between the real point and the predicted point, so that the distance should be minimal. Okay, so if I will just mark it here, okay, if I will just mark it here at this point, so this is my predicted values for this one. Okay, this is my predicted point for this one, this is my predicted point for this point, and this is my predicted point for this one, and for this one I have here. Okay, so this is nothing but, this theta value is nothing but it is my coefficient. Okay, this is my coefficient I have, and this is the intercept I have, or I can tell it as this is the slope, right? The point where my x-axis and my y-axis are intersecting. Okay, that is nothing but that is my, if I will make an angle here, so this is nothing but this is my slope. Okay, now what I have to do, I just have to do the summation of these distances. Okay, I just have to do the summations of these distances, means between my real value and between my predicted value. Okay, so this summation, what it will do, now it will, we are going to do the summation in such a way that the summation of this particular distances will be approximately equal to 0. Okay, that means if this distance will be approximately equal to 0, that means what? My real point will be equal to my predicted point, right? And when my real point is equal to my predicted point, when this happens, at that time, I can call it, this is my best fit line. Okay, this is my best fit line. Now, what is the formula of this cost function that we are going to use? That is nothing but j of theta 0 comma theta 1 equals to, okay. First of all, I will tell you that this line, the equation of this line is nothing but s theta of x equals to theta 0, okay, theta 0 plus theta 1 into x. Okay, theta 0 and theta 1 into x. This is nothing but what? If this is my y, okay, this is my predicted point, right? This is my y, and this is nothing but c plus m into x, right? Or I can write it as mx plus c. So this notation I have just changed according to the machine learning algorithm. This mx plus c has got written as like this, theta 0 plus theta 1 into x. Okay, so basically we need to interchange this theta 1 and theta 0 value. Okay, so then what are the parameters? That is my theta 0 and my theta 1. Right, the parameter is nothing but that is my theta 0 and theta 1. And what I need to find, I need to find a best value. Okay, I need to find a best parameter value, that means best value for this theta 0 and theta 1, upon which, by use of which the distance of my predicted point and my like real point would be minimum. Okay, it will be my minimum. So my whole equation, if I will say, my whole equation revolves around the interchange of this theta 0 and theta 1 parameters. Getting it, everyone? Now, suppose, okay, so if I will write my cost function, then my cost function looks like this one. Okay, my cost function looks like this one. So this is nothing but j theta 0 comma theta 1 equals to 1 by 2m summation of I equals to 1 to m s theta of x of I minus y of I whole square. Okay, so if like it will be not be visible, then what I will do, I will write it here itself so that it will be easy for you to understand. Okay, so my cost function is nothing but it is j of my theta 0, okay, comma theta 1 equals to 1 by 2m. I will tell you why we are using 1 by 2m. Okay, 1 by 2m summation of I equals to 1 to m. M is nothing but what? M are my all the data points. Okay, this summation of I equals to 1 to m means what? I have to do the summation from the first data point to all my data points. M are nothing but M are my data points. Okay, so 1 by 2m summation of I equals to 1 to m. What I have to do the summation? I have to calculate the distance and I have to do the summation. What will be the distance? So this my predicted point is nothing but what? H theta of x of I. Okay, S theta of x of I minus y of I. Y of I are nothing but these are my actual points. Okay, whole square. Now, two things here come. What two things here come? Now, first of all, why we are squaring it? Why we are squaring it? To not to get any negative values. Okay. or I will write it as for non-negative values. Okay, for non-negative values. Now, the second thing is that why we are doing this 1 by 2m. Okay, why we are doing this 1 by 2m. So, this 1 by 2m is nothing but we are doing it for the derivative purpose. Okay, 1 by 2m, we are doing it for the derivative purpose. Okay, and when you will go, when we are updating the theta 0 and theta 1 value, okay, when we are updating the theta 0 and theta 1 value by using our gradient descent algorithm, at that point of time, whenever we are doing the derivative, our work will be simpler. Because if I will say derivative of, okay, derivative of x square, it is nothing but what? Derivative of x square will be what? 2x, right? Right? Here I have 2x and here I have 1 by 2m. Yes or no? 1 by 2. Just like remove this m. 1 by 2. So here it will be 1, 2 to cancel. So what it will left? Only x will be left, right? That means what? My calculation is getting simpler, right? That's why we are using the derivative here. Okay, that's why we are using the derivative here so that my equation will be get simpler. Okay, and if we will know, this is my cost function, right? Now, when you are doing the cost function, okay, when we are doing the cost function, so that I will make you understand with the example. Okay, that I will make you understand with the example. So this is my gradient descent algorithm. So before going towards the gradient descent algorithm, what I will do, I will make a new share of the whiteboard. Maybe like it will be visible to all of you, right? So let's take, we have my cost function that is 1 by 2m, right? Summation of I equals to 1 to m is theta of x of I, x of I minus y of I, okay? And that is whole square, right? Now, let's take, assume my theta value, okay? My theta 0, assume that my theta 0 equal to 0. Right? Assume that my theta 0 equal to 0. Now, what will be my s theta of x then? What will be the value of s theta of x then? As I told you, what is my s theta of x? S theta of x is nothing but that is what? Theta 0 plus theta 1 into x, right? Theta 0 plus theta 1 into x. Guys, don't go like with my handwriting. It is very bad. So, now, if my theta 0 is 0, I have put my theta 0 is 0. Then what is my value for the theta, s theta of x? That is nothing but theta 1 into x, right? Theta 1 into x. Yes or no? That means if I will draw a graph here, okay? So if I will draw a graph here, if my intercept is 0, that means what? My line is passing through the origin, right? My line is passing through straight through the origin. This is my theta 1 into x. This slope, yes or no? Passing through the origin. Now, suppose I have some data point. Let me assume I have some data points. Okay, that is 1 comma 1, 2 comma 2, 3 comma 3. Okay, just I will take it this one only, and I will do the graph for this one. Okay, so here I have something 1, 2, and here I have 3. Okay, here also I have 1, 2, and here I have 3. Okay, now tell me when my s theta of x is theta 1 x, that means when my theta 0 is equal to 0. Let's calculate the cost function here. Okay, j of theta 1, right? Because I don't have my theta 0. Theta 0 is equal to 0. So I will take only the cost function for my theta 1, right? So what I will do? 1 by 2m. So summation of I equals to how many data points I have? 3, right? 1, 2, and 3. I will write it here 3. Now, so theta 1 into x, right? Theta 1 into x it has given. Now, tell me that what will be when, that means when my line is passing through the origin, that means what? This point, my x point is equal to my y point, if I will say, that I can say, right? If my line is passing through the origin, that means I can say that, okay, my actual point and my predicted point are same. So if I will do theta 1 into x, then what will be, it will be nothing but 1 minus 1 square, okay, s theta of x minus y, then 2 minus 2 square, 2 minus 2 square, okay, plus 3 minus 3 square. Okay, so it will be entirely 0. Okay, so this is for, if I will say, when theta 1 is equal to 1, let's say, let me assume this one, let's theta 1 is equal to 1. Okay, when theta 1 is equal to 1, that means what? What will be my data points then here? What will be the value for my s theta of x and y? So I know that s theta of x equal to theta 1 into x. What is my theta 1? That is 1. Right? So 1 into 1. First it will be 1. Then 2 into theta 1 into 2. Right? 1 into 2. It will be 2. Then theta 1 into 3. 1 into 3. That will be 3. Okay. So what will be? This is my nothing but these are my s theta of x value. S theta of x value. So S theta of x is nothing but first we have 1 for this first data point. 1 minus what is my predicted data point? That is 1. Then like that only 2 minus 2, 3 minus 3. Okay. So when my theta 0 is equal to 0 and my theta 1 is equal to 1, what is my cost function here? I got that is 0. Right? That is 0. So if I will do a straight line here, if I will make a straight line here, right? So it will be like my data points will be, so here I will do it in a like, okay. So my data point will be this one for 1, 1, for 2, 2, this one, right? And for 3, 3, this one, right? Because here my cost function is 0, right? And when my cost function is 0 means what? My actual point and my predicted point are same. There is no distance between my actual points and predicted points. Understood or not? So now let me draw the cost function graph. Let me draw the cost function graph here. My line will be somehow tedha medha. Don't get to this. Okay. So here what I will do, I will give the data points as, suppose this is my 0.5. Okay. This is my, suppose, not write it here 1. So this is my 0.5. This will be my 1. Okay. This will be my 1.5. 1.5. This is my 2.0 and so on. Okay. So this one I will do it because like as we are just hand making this thing, so we have to like draw it in a perfect manner. Okay. So this will be my 1. Okay, this particular point will be my 1. Now here also I will get that is 0.5. 0.5. Here I have 1. Here I have 1.5. Then here I have 2 and so on. Here I have 2.5 around. Okay. So when, now tell me when my theta 0 equal to 0 and theta 1 equals to 1, right? When my theta 0 equal to 0 and theta 1 equals to 1, that means what? This point. When my theta 1 equals to 1, this point. So it is passing through my origin, right? It is passing through my origin, yes or no? So that I will do it here. It is passing through my origin. This is my cost function. Okay, when my theta 1 is 1, what is my cost function? That is 0, right? That means what? This axis it will be. Understood? Now, what I will do, I will do a next scenario. Okay, I will just take another scenario that will be what? Let's take the value of theta 1 equals to 0.5. Okay, so when my theta 1 value is 0.5, my cost function, if I will calculate, then it will be around how much? My cost function will be approximately 0.58. Okay, if you will calculate this, it will come around this one. Okay, so this will be how much? If my theta 1 is 0.5, that means what will be my theta 1 into x? That will be 0. For first data point, it will be how much? 0.5 into 1, 0.5, right? For the second one, for the second data point, 0.5 into 2, that is 1. For the third one, it will be 1.5, right? For third, it will be 1.5. This is my data points. Just subtract it from the actual point, it will it will give you this one, 0.58. Now, if I will do 0.58, that means when I am taking the theta value as 0.5, what will be my value here? This one. And my cost function is 0.58. It will be around this one. Okay. It will be around this point, or like somehow down, little down, around this point. Okay. Like that, when I will take theta 1 value, okay, theta 1 value is 0. Suppose I will take my theta 1 value is 0. Okay. That means what will be my new data points? What will be my like s theta of x? What will be my s theta of x point, my predicted point? That will be how much? 1 minus 0, sorry, 0 minus 1, or sorry, I will do, that is theta 1 into x, right? Theta 1 into x. That means it will be 0, 0, and 0. Okay, if we will go and subtract it by using this one, this formula, then my cost function will be around, approximately it will be around 2.3. Okay, it will be approximately around 2.3. That means when my this one, when my theta 1 value is 0, this is my 0, right? When my theta 1 value is 0, my cost function is around 2.3. It will be around this one. Okay, now if I will go and join this whole the points, okay, if I will just go and join this whole the points, it will make a curve like this. Okay, it will make a curve like this. Here it is nothing but this is my global minima. Why I am making you understand this concept? Because this is, it will be getting used when, if you will not understand this concept, then you are not going to understand how like linear regression can't deal with the logistic regression. Okay, if this is my global minima and this entire curve is known as my gradient descent curve. Okay, this entire curve is nothing but it is my gradient descent curve. Okay, so here what we are doing, now look, this is my theta 1 point, this is the cost functions, right? We are starting from one point and we are calculating the cost functions, okay, and we are making this curve, yes or no? That means what we are doing here, we are interchanging our theta value. First I have taken my theta 1 value as 1, then I have taken 0.5, then I have taken 0, right? So what we are doing, we are interchanging our theta 1 value, our slope value, right? That means in LR, in linear regression, we have to start with one point. Okay, we have to start from one point. Suppose if I will give this is my 1 point. Okay, that means we have to start with one theta 1 value. Okay, and what I will do, I will update my theta value. I will update my theta value so that it will come and reach towards the global minima. Okay, to particular disposition, to particular disposition. When, at what point or at what theta 1 value I am reaching this global minima. Okay, if you will go and take this theta 1 value and construct your theta 1 value and construct your line, that is theta 0 plus theta 1 into x. Okay, if you will go and construct the line by using this particular theta 1 value, theta 0 plus theta 1 into x. So at that point of time, you will get the best fit line. Okay, so this is my best parameter. That means this is my best theta 1 value, and by using this theta 1 value, I am going to, whatever line I will create, okay, I will make, that will be my best fit line, where my predicted values, where my distance between my predicted values and my real values are less. Or I can tell that what is my real value that I am getting and what prediction I am doing, that is equal. There is no difference, or there will be a very little difference between them. Okay, got it now? So this is what the algorithm says. Now, one thing, whenever we are doing this one, like updating the theta 1 values, how we can updating this theta 1 value? By using the gradient descent algorithm. Okay, by using this, I will write this as the GD algorithm, okay, or the gradient descent algorithm. Now, what this algorithm says, now it acts upon the while loop. That means until and unless your condition will get false, it will constantly do the iteration. Okay, so what this tells, to update the theta 1 value, instead of using different theta 1 values manually, we have something called as this gradient descent algorithm, or we can also call it as the convergence algorithm. Okay, convergence algorithm. Okay, now what this algorithm says, now repeat until convergence. Repeat until convergence. It will take in a while loop. Okay, so it will be theta j of theta j minus alpha, okay, alpha of derivative of theta j with respect to j theta 0 comma theta 1. Theta 0 comma theta 1. Okay, now this alpha is nothing but this is my learning parameter. Okay, this is my learning rate, not learning parameter. I will say it as a learning rate. Okay, that means when this learning rate will specify by what speed my this theta 1 value will come to the global minima. Okay, that it will specify. Understood? Now, if I will go and check it here, so not so. If I will do a parallel, I will draw a line to this axis, then this will be my direction, right? This will be my direction. So it is a negative direction to reach my global minima. Same here, if I will do a slope here. Okay, suppose for this point, if I will do a slope here and I will draw a parallel line here. So this will be the direction, positive direction, right? To reach my global minima. Yes or no? So at that point of time, we have to update our theta 1 value in such a way that for the negative slope, okay, for the negative slope, my theta 1 value will be theta 1 minus alpha of negative. Okay, that means if negative will get multiplied, it will be a positive number, Okay, it will be a positive number. The second one is for theta 1 plus alpha into a positive number. Okay, this is the two condition I have. That means if I will say, and what is my this learning rate value? That will be, it will be like decided by the domain expertise who will be present over there. So basically we take this learning rate value as 0.001. Okay, 0.001. Now, so if I will say what is my total, like what is my final gradient descent algorithm, then I will write it as derivative of j theta of theta, j of theta 0 and theta 1, if I will write it as theta 0 comma theta 1. Okay, if I will write it as, then derivative of my cost function, okay, that is 1 by 2m summation of I equals to 1 to m, then s theta of x of I minus y of I, right, whole square, right? And we know that my j value should be 0 and 1 because I have theta 0 and theta 1. So my value will be 0 and 1, right? If I will do it, so if j is equal to 0, if j is equal to 0, then what will be my equation here? The 1 by m summation of, sorry, not it's an equal to, okay, so it will be 1 by m summation of I equals to 1 to m s theta of x of I minus y of I whole square. Okay, if j equal to 0. If j is equal to 1, what will be my equation? Okay, if j is equal to 1, then my equation will be 1 by m summation of I equals to 1 to m. Okay, summation of I equals to 1 to m s theta of x of I, okay, plus y of I, that is whole square, or I will say s theta of x of I minus y of I into x of I. Okay, so if I will just split it, we know if I will derive it, then this will be nothing but what? S theta of x is nothing but what? Theta 0 plus theta 1 into x, right? Theta 0 theta 1 into x. Understood? So this is my complete gradient descent algorithm. So by using this equation, what we are doing? We are adjusting our theta 1 parameter, theta 0 and theta 1 parameter in such a way that my theta 1 value will reach to the global minima, and with which theta 1 value I am reaching to the global minima, that particular theta 1 value will be taken as the best slope, best possible slope, and upon that only we are going to build our best fit line. Okay, so this is the complete equation I have told you regarding this linear regression. Okay, regarding this linear regression. Now, what is the problem? Here we can easily do this, right? Then after building this base fit line, we have to check the performance of our model with the training and the testing part. Okay, so that is a separate thing, the performance of our model by using the R square and the adjusted R square. Then we have to do, if like my performance is not getting that much of well, then we can use the regularization methods. That is our L1 and L2 regularization and the elastic nets. Okay, then what is the problem with this linear regression? Okay, this is for the classification, this is for the regression problem that I am using. And we know in regression, we have the continuous variable, right? If I have here age and if I have here weight, okay, suppose, so if this is my age and if this is my weight, so it will be continuous variable. We just have a continuity here, right? We will have a continuity here. But in classification problem, we know that in classification problem, we have something called as the probabilistic methods. Okay, the classification problem is completely based on the probabilistic theory. That means, suppose if I will say that, okay, today, okay, if a person is like, a very general example I will give. If a person is studying for like 6 hours, okay, he is playing for 2 hours and he is sleeping for like 10 hours, then whether that person is going to pass or fail in the exam, right? So if that I will say that, okay, he will pass because he is studying for 6 hours and very less hour he is playing, right? So it is a what? It is a probability condition. We are giving the conditional expenses, and according to that, we are extracting the result, or we are interfacing the result that whether it will be going to be like pass or fail. Okay. Or suppose I have some characteristics of a human being, and according to that, I will go and I will check that, okay, either he is a female or a male. If a person is diabetic or not, how can I will like tell? By checking the symptoms. Right. So the symptoms are nothing but there. I can make it as, okay, these are the variables. How many times he is sleeping? What is his urinary conditions? What is his blood sugar level? Okay. Like what is his diet plan? According to it, I can like tell what is the day-to-day activities that is completely regulating his or her body. According to that, I can tell that, okay, that person is diabetic or not. Right. So this is the classification based problems, where we have both the binary classification and we have both the we have the multi-class classification. Okay, in binary classification we just have two outputs that will be either 0 or 1. Okay, so what I will do, I will just clear it and I will do the share to return to our slide. Okay, so this is my gradient descent, this is my cost function. Okay, now here it is the formula also I have given. Okay, so whenever we are suppose this is my one initial point, okay, and we are giving the slope. So basically this point will come to my global minima, okay, or it is not called as a global loss minimum. So to update this path, to update this theta1 value so that it will come to this global minima, we use this function. Okay, so here we have the weight minus d loss by dw. This is nothing but what? That the equation we have used. The same thing, it has just given in a new notation, in another notation, don't get confused. Okay, so this is my theta1 minus alpha d of what? J of theta 0 comma theta1 divided by d of j. Right? Now, if I will say the linear regression for the classification problem, okay, for the classification problem. Now, look at this point. Suppose here I have one data point, was some data set. Okay, here suppose I have some data set like, if I will say number of study hours, okay, number of play hours, okay, and the number of sleep hours. The same example I'm giving. And here I will give the output as pass or fail in the exam. Okay, so suppose this person is like studying for like more than like, okay, first I will give, suppose this person is studying for 2.5 hours, okay, he's playing for around like 4 hours, okay, and is sleeping for 6 hours. So obviously if he is studying for 2.5 hours, that means he will fail. Suppose this person is like studying for 4 hours, okay, then he is like playing for 2 hours and he is sleeping for 6 hours. Okay, then I will say that, okay, this person will pass. Suppose this person is studying for, suppose another person is studying for 6 hours, he is playing for 1 hour and he is like sleeping for 8 hours. Obviously he will be passed, right? If a person, the next person is studying for 2 hours, he is playing for around 5 hours and is sleeping for 10 hours. Obviously this person is going to fail, right? Suppose this is my data set I have. Okay, this is my data set I have. Now, if I will just plot this into a graph, how it will look like. Okay, so this I will like take. Okay, what is my measure? Okay, this particular my pass or fail output. This is completely depending upon what my sleep number of study hours, right? Yes or no? So let's take this feature. Let's take this variable and plot my graph of the logistic regression graph. Okay. Now this is my graph, right? Here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 here. Okay, and this graph is nothing but this is my fail. Okay, pass is my what is my I will note the fail as 0 and I will note the pass as 1. Okay, so this is my fail, this is my pass, right? Now if I will go and check for this 2.5, right? That means if I will go and okay, so this is my 2.5. If I will say, I will just create a line here, okay, in between this. If this is my 0, this is my 1, then the midline will be my 0.5, right? My midline will be my 0.5. Now, if I will do a line here, so this is, I have done a boundary. Okay, this is my boundary. That means what will happen, I will say you how, why I'm telling it as a boundary, because above this 0.5, whatever the observations will become, that observation is nothing but that will be passed. And below this 0.5, whatever observation will become, that will consider it as a fail. Okay, it will happen. Okay, it will happen. Now check for this 2.5. If I will do a point here and I will just mark up draw a line, then it is falling behind, like below this 0.5. That means what? The person is going to fail. Now if I will just give 4, right? 4. Now if this is my straight line, suppose I have drawn here. Now to this one, okay, to this one, if I will join this one and if I will join this one, then according to my scenario, if a person is studying for 4 hours, that means he will pass, right? Yes or no? But whenever I'm plotting it upon this straight line, upon this graph, what is it? What is the result it is giving me? It is below, it is coming below my boundary, 0.5. That means according to the graph, that person will fail. So here, my prediction and my real points are completely different. Right? That means the person in real, actually the person will get passed. But whenever we are predicting that part, what is the prediction it is telling? It is telling me fail. Okay, now go for the person who is having like studying for 6 hours, right? Now to it, suppose this is the point 6.5, suppose I am taking. Now this is the point, right? And this is the point. Now also, that means what? If a person is studying for 6 hours, he will fail. No, right? This is a very bad condition, right? This is a very bad condition. Now, the third scenario, suppose tomorrow an outlier will come. Suppose tomorrow one person will come who is studying for around 12 hours, right? Who is studying for around 12 hours. Then suppose this is the point. Now if I am just making the line, right? This linear line, what it will do? It will just go beyond my graph. When coming an outlier, right? It will go beyond my graph. So basically, what are the limitations? Now, linear regression is completely based on the continuous variable, but classification is based on the probabilistic scenarios. So linear regression can't work with the probabilistic scenarios because this is what the problem occurs. Okay, this is what the problem occurs. The second thing is that linear regression is very effective with the outliers, or I can say it is completely affected with the outliers. As I told you, suppose one outlier will come, the line will go beyond the graph. Okay, the slope will be like 90 degree or it will be like 180 degree somehow. 90 degree it will make. Getting? This is a very bad condition. We can't use linear regression for this purpose because in classification outliers come. Okay, so what we need to do, what is the solution for this? What is the solution for this? Now we have to, whenever we are dealing with outliers or whenever this situation come, we have to flatten our line. Okay, at a point we have to flatten our line or we have to square our line. Okay, this term is nothing but we have to square the line or we have to flatten the line. Okay, so for this scenario, okay, to flatten our line, we use the sigmoid activation function. Okay, we use the sigmoid activation function. So this is nothing but where logistic regression comes into picture. Okay, where logistic regression comes into picture, and logistic regression is completely used for the classification problem. This is the only algorithm that deals with the classification problem only. Okay, this is a regression algorithm, but it deals with the classification. So what does this logistic regression say? Now, the graph that will be made by the logistic regression, that will somehow look like this. Okay, so from this point we will be just squashing our line, we will flattening our line. Okay, this is nothing but this is my g of z. Okay, this is my positive, this is my negative, right? Suppose if I will get some other positive values also, look, suppose if I will get an outlier here at this point, what it will do? The line will extend towards this only. It will not go beyond your graph. Okay, the line will just extend toward this. Suppose I will get a negative value. So what it will do? The line will get extends toward this one. Okay, so for this passing of line, we use something called as sigmoid activation function, that is g of z is equal to 1 by 1 plus e to the power z. So this e to the power z is nothing but it will be what? I will write it the equation it like this, 1 plus e to the power, okay, 1 plus e to the power, I can write it as theta 0, okay, minus of theta 0 plus theta 1 into x. Okay, so basically this one is minus z. Okay, I can also write it as 1 plus e to the power minus theta 0 plus theta 1 into x. Okay, so here two condition will appear. If y is equal to 1, okay, that means my pass value, my pass or fail value, it is okay, the output value. Y is equal to 1 if my s theta of x is greater than equal to 0.5. That means if my s theta of x value will be greater than 0.5, then my output will be 1. If it is less than 0.5, my output will be 0. Okay, so we can also call it as, like, we can also conclude that when y equals to 1, theta transpose of x is less than 0, like greater than equal to 0, and y equal to 0 when theta transpose of x is nothing but what it is, less than 0.5. Okay, so this is the solution for the classification problem when we are using. What we will do, we will just make this straight line, we will just square it. Okay, we will just square it to this. This is my linear regression straight line. This is my logistic curve. Okay, this is my logistic curve, sigmoid activation curve. Okay, so for this we have, and also for the logistic regression, we can't use that linear regression cost function. We can use that, but what will happen? Now it will stuck in the local minima. Okay, that local minima, global minima you have understood. Local minima is nothing but if I will just do a graph here. Okay, So my local minima will be something this. These are my local minima. If local minima will happen, then you can't reach to your global point. Okay. So this will happen. So for that, what we are doing now, we are using two type of this is my non-convex functions. Okay. So for that, in logistic regression, we use two cost functions. Okay, one is for pass and one is for fail. And if we will go and see, if I will just make that graph here, so that graph will look like something this. If I will make the graph, so for the one, okay, for the value one, the graph will something look like this. So this is my s theta of x here. This is my cost function graph. Okay, so it will be like this. Okay, and another one, it will be, just give me a second. Okay, another one, it will be like 0. Another will be, it is for the 0. I will say this graph will be for the 0. Okay, if you will just merge these two, if you will be merge these two, then you will be getting the cost function of the linear function. That will be, you will be getting the what global minima here, the best possible point. Okay, this is my cost function graph for the logistic regression. Logistic regression. Okay, so this is how, this is all the things that we are going to, like we have discussed in the today's orientation session. And one for first thing first, the theoretical part, as I have discussed with you, that what is the, so why we can't use the linear regression. We have three main motives. That the first thing first is that the linear regression can't deal with the probabilistic values. Okay, it always comes with the continuity variables. Second one is, it is completely affected by the outliers. Okay, and third one is, it will not give you an accurate prediction, like when the probabilistic uh, computation will be there. Okay, this is three things that we use. And for this classification problem, we use the like logistic regression for the binary classification, and we use the softmax regression for the multi-class classification. Okay, everyone. So this is for the today topic. Look at here. This is the graph. This is the difference. Okay. So you have to squash this line. When you will squash this straight line, it will somehow look like this one. Okay, so thank you all, and thank you for joining this session. So let me stop the recording first.